Internet had a bit of an oopsie, a bit of a landmine, a bit of a mistake that happened that caused a lot of the internet to go down for 3 hours on Thursday. This site here, Down Detector, this is an image of Down Detector at the time the outage began, where a lot of major services that everyone uses like Spotify, Google, AWS, Cloudflare, these huge cloud providers are all seeing outages at the same time, which effectively took down a majority of the internet for about 3 hours, at least in the US. Some other services that are downstream affected, like Claude, for example, Twitch, NPM, Dragon Ball randomly were all hit. The scary part about outages like this is it kind of shows a natural vulnerability in like the design of the internet as we know it. I want to talk about that and how a minor kind of hilarious programming error is the root cause of this issue. On Thursday, the internet went down, nothing too crazy going on here. Basically, we just know that for a short period of time, people were not able to use the internet as we know it. They're not able to use basic services that they typically log into like Google, AWS, Gmail, all of these very basic things. Low-Level Academy, my course website, for example, also was affected by this outage downstream. Every time the site gets a 500 error, which is what happens when you log into Google when it's down, I got an email. So I got 100 emails in the span of 20 minutes. Not a great place to be as a solo sysadmin. Now, there was speculation for a long time that this may have been a cyber attack, right? Attacks like this are becoming less and less common, but they do still occur. One of the bigger ones that were sort of like this, that like actually took the internet offline for a series of hours, happened in 2016 when Dyn, a major provider of DNS for the internet, got taken offline by this thing called the Mirai botnet. So when the Google outage was happening, people were like, oh my God, it's another cyber attack. And at this point, I think like Israel had bombed Iran by then, and so maybe they were thinking that Iran was retaliating. It was a bunch of crazy stuff like this. And eventually it turns out it was something even sillier than a cyber attack. Google, being the downstream cloud provider that caused this incident, and again, this isn't me shitting on Google, these things happen, it just kind of is funny that like the nature of the bug here, they put out their incident response and they describe in this post here, Google and Cloud APIs are served through the Google API management and control planes. Distributed regionally, these management and control planes are responsible for ensuring each API request that comes in is authorized and has the appropriate policy and appropriate checks like quota to meet their endpoints. When they're saying control planes and management planes, basically all this means when you're talking on the internet, right? When a packet traverses the internet, the router has this thing called a data plane, which is the place that the data goes. Your packet for your request to google.com is traversing the data plane of these routers. Now, the routers are configured to do something. The routers have routing information. The routers have passwords enabled for you to log into them if you're an administrator of that network, but they never want to give you access to that stuff, right? That'd be silly for you to be able to log into the router. So that other area where the admin can control the routers is the management plane or the control plane. Now, the core binary that is part of this policy check system, so again, the policy checking being, is this request that is going to the API authorized for this person? Are they allowed to ask for the thing they're asking for? Now, this binary that's running that process, the program that literally executes that check, is called service control. Service control is a regional service that is a regional data store and that it reads quota and policy information from. This data store metadata gets replicated almost instantly globally to manage quota policies for Google Cloud and our customers. So here you have basically policy and quota rules getting checked on requests, right? So quota being how many requests can you make, and then policy being are you allowed to make those requests, right? Making sure that the requests that you're asking them, a cloud provider, is allowed to be asked. Now, on May 29th, 2025, which is well before this, a new feature was added to service control, again, the data plane program, for additional quota policy checks. This code change and binary release went through our region by region rollout, but the code path that failed was never exercised during this rollout due to needing a policy change that would trigger the code. As a safety precaution, this code change came with a red button to turn off that particular policy serving path. Okay, so the reason why this was released on the 29th, but it did not occur until the 12th, is because that path in the code that had the bug, and they're getting into the bug here in a second, never got hit, right? And also, by good design, they literally designed a red button or like an emergency kill switch into the system that, hey, if that code path is broken for some reason that we did not detect, let's hit that red button to kill it so that it can't take down the internet. Obviously it did anyway, but at least they had that in the back of their minds. Without appropriate error handling, a null pointer caused the binary to crash. This is what is so crazy about this entire scenario to me, is that it is a null pointer dereference that took down the internet. I will say this again, for those of you that are well-versed in programming. It is a null pointer dereference that took down the internet in the US for about 3 hours. If you're not big on programming, let me show you what I'm talking about. Before we do that, let's talk about the sponsor of today's video. It's me again. Hi guys. I honestly believe that if you're a programmer trying to write fast, effective code, or you're a cybersecurity professional trying to stop your stuff from getting attacked, all of these require you to know the basic fundamentals of computers. My courses on Low-Level Academy teach you languages like C, networking in C, threading in C, assembly, and even a new installment, Rust, to learn the basics of how computers work. And Zero to Hero C programming will teach you the basics of the C programming language, the language that runs all other languages, and you can even learn arrays in C right now for free. Go check that lesson out. If you want to learn assembly, my ARM load operations lesson is also free. And I also have a free 3-day C course that you can check out right here on the landing page. Guys, if you want to be a good programmer, you got to know the fundamentals. And where do you learn the fundamentals? On Low-Level Academy. All right, guys, back to the video. See you there. A null pointer dereference is something you've definitely experienced if you've programmed ever. If you're not a programmer, I will explain it to you right now. It is very simple. In programming, you have these things called pointers. They are literally just variables that contain memory addresses. They point to other things. So here we have a character pointer that is called not null, and it points to the string hello. Okay, very simple. The value not null is the address of this hello string. Easy. Okay, the problem child here is this pointer called null, which has the value of null, which is literally just 0. There is a whole argument in the C community about what null actually is in terms of value and type, but what you can think about it as is just the number 0, okay? And because there is nothing mapped into the process at the number 0, if you try to access memory 0, you will crash your process. I can show you that right here. We're gonna print the string not null and null. Printf actually will check for this to be null and print the word null and not crash. But if I try to like edit the string, for example, this will crash the program. So I run the program null, boom, so we say hello, null, we print it, but we then crash the program. And so you may be thinking, well, how does that happen? How could a null pointer exist? Remember, this is a binary that is parsing policy and quota information, right? So maybe there's a JSON object floating around that has the data fields he, and OMG. And somewhere in the program, it's looking for a field and it's gonna extract that number that has quota data out of that object. Well, oh no, in the program, we're not actually looking for the he field, we're looking for the haha field. And because the haha field, it is not shown in the JSON object, when I do, JSON lookup from object the haha field, this will return a null pointer. And if I'm not checking for that null pointer in the code here, and I go to access it later, that will take the binary down. This is a null pointer dereference. It is standard stuff in the world of programming. It is so simple to write code that you fail to check a null pointer, maybe because an API doesn't declare that it could return a null pointer, and then bada bing, bada boom, you're taking down the internet. So without appropriate error handling, the null pointer caused a binary to crash. Feature flags are used to gradually enable the feature region by region per project, starting with internal projects to enable us to catch issues. If this had been flag protected, the issue would have been caught in staging. So this idea of feature flagging is very simple. Basically, when you create a new feature in a program, you have some management plane API where you can turn that feature on internally, then in staging, then region by region. You slowly allow the feature to go into the world over time instead of just dumping it into reality. And that very slow, gradual release allows you to see these errors ahead of time. And if you catch them early, you hit that red button and turn it off. Unfortunately, the service control changes were not bound by feature flag, probably because this is an internal management plane thing, not like a user-facing feature. So it kind of makes sense that in some cases, maybe you don't want to feature flag it because you know it's only for Google. It's not for the average consumer. Now, this is just the nature of the vulnerability that got hit. Here's actually went down. So on June 12th, 2025 at roughly 10:45 PDT, so 13:45, 1:45 PM EST, which is when I experienced it, a policy change was inserted into the regional spanner tables that service control uses for policy. Given the global nature of quota management, this metadata was replicated globally within seconds. This policy data contained unintended blank fields, hence the null pointer dereference. Service control then regionally exercised quota checks on policies in each regional data store. This pulled in blank fields for this respective policy change and exercised the code path that hit the null pointer, causing the binaries to go into a crash loop. This occurred globally given each regional deployment. So literally what happened is they sent this binary out globally. Everyone got this binary. They put out a policy change on the management plane that contained a blank field. The service control binary did not account for that null pointer that came off of that blank field. And because there was no feature flagging, it had already been fully released. This hit every version of service control, took down Google Cloud. Now, luckily, this is where it's kind of cool, right? Within 2 minutes, our SREs, our site reliability engineering team, was triaging the incident, and within 10 minutes, the root cause was identified, and the red button to disable the serving path was being put in place. So again, don't forget, it may not have been feature flagged, but it was red buttoned, which means that they have somewhere in a management plane to just boom, hit that button, turn that baby off, and like we're good to go. Within 40 minutes of the incident, so we are not even an hour into this problem, the red button rollout was completed, and we are starting to see recovery across regions, starting this with the smaller ones first. Okay, so feature was flawed, bada bing, bada boom, like we are out here fixing it. Within some of our larger regions, this is where it gets kind of like the meta analysis of like red buttoning and like traffic in a cloud environment like GCP. You have to really like it's kind of mind boggling. Within some of our larger regions, such as US Central 1, as service control tasks restarted, they created a herd effect on the underlying infrastructure it depends on, like the spanner table overloading the infrastructure. So what's happening here is all of these service controls live across the world, right? They are hitting the red button to kill them, to restart them. And because they are all restarting at the exact same time, they are completely nuking the resources of the underlying infrastructure, like that spanner table that spans out the policy. And it's just completely unable to come back to life because there's no process to determine how long it should wait to give other people the opportunity to come back up, right? The service control did not have exponential backoff implemented to avoid this. So yeah, it took up to 2 hours and 40 minutes to fully resolve this in US Central 1 as we throttled back task creation to minimize the impact on the underlying infrastructure. At that point, the API was fully recovered across all regions. Now, obviously, Google has been very apologetic about this since this incident happened. It is their fault, like they made it happen, but they've been very transparent about how it happened, about the errors and their ways, and they've been very like apologetic because again, this took down a lot of the internet for around 3 hours last week. I want to kind of highlight that like I love cloud providers. I have Low Level Academy. I have a bunch of other projects that I host that I do not have to have in my house. I can put them onto the internet, which is just somebody else's computer, and it's pretty cool. It's just a really great way of computing. However, the nature of the internet's single-handed dependence on one or two cloud providers is kind of scary. It definitely creates this like single point of failure where like if Google goes down for a couple hours on a Thursday, the majority of the internet, I mean, to include myself, right? Like my own platforms use Google Cloud. The majority of the internet falls off the face of the earth. It's just kind of, it feels like it goes against the original, Triple L, hello. It feels like it goes against the original design of the internet, right? This like weird kind of like mesh network of nodes that if one were to go down, okay, cool, we have routing in place. We can see that the metric on that link went way up. So we're gonna go around that. You're doing some Dijkstra's. I'm an electrical engineer, probably got that wrong, but it's fine. My point is, I feel like not that we've lost the path, but that we need to think long and hard about our dependence on sole points of failure, and if we're willing to risk the future of the internet on like these single pivot points, because it just feels counterintuitive to like the design of this whole system. Anyway, you're probably wondering, wow, Triple L, that's pretty cool, or wow, Low Level, that's pretty cool. Would Rust have fixed this? Probably not, maybe. So Rust does have a couple cool features. Rust has some cool features, right? Rust doesn't actually have a null value. It has this idea of options where things in a structure like have to have a value, but you can also make them options where they either are some value or none value. So an option of I32 is sum of one, which means it's a one value wrapped in some type, or it can be none, right? That is a legal option for the type of an option, or a legal value for the type of an option. Now, the issue, and again, you should not be using unwrapped. This is like bad Rust. I'm just saying, like, people think that Rust is this language that is like immune to error. The language is fully well and capable of creating at least a DOS condition where if you do something weird, like you unwrap, or like you have an array and you do like, that array of some value outside of its size, you can easily send the process into a panic, right? You can do cargo run, and you'll see that this panics with you're unwrapping a none value because we did an unwrap operation on an option that has no value inside of it, right? So like it's not a null pointer dereference in the same way, but you are able to write code that can crash. So is this an exploitable condition that someone can take over? No, neither was the other one, but you can DOS this. And if this kind of code existed in GCP, would have the same effect. So, you know, would Rust fix this? Not necessarily. Anyway, guys, that's it for now. Thanks for watching. I appreciate it. If you like this video, if you like doing this kind of stuff with me, hit that sub button. I really appreciate it. And then go check out this video that I think you will also enjoy just as much. See you over there. Goodbye.